A supercomputer is a computer at the front line of contemporary processing capacity, particularly speed of calculation, which can happen at speeds of nanoseconds. Supercomputers were introduced in the 1960s, made initially and, for decades, primarily by Seymour Cray at Control Data Corporation, Cray Research, and subsequent companies bearing his name or monogram. While the supercomputers of the 1970s used only a few processors, in the 1990s machines with thousands of processors began to appear and, by the end of the 20th century, massively parallel supercomputers with tens of thousands of off-the-shelf processors were the norm. As of November 2013, China's Tianhe 2 supercomputer is the fastest in the world at 33.86 petaFLOPS, or 33.86 quadrillion floating-point operations per second. Systems with massive numbers of processors generally take one of two paths. In one approach, a large number of discrete computers distributed across a network devote some or all of their time to solving a common problem. Each individual computer receives and completes many small tasks, reporting the results to a central server which integrates the task results from all the clients into the overall solution. In another approach, a large number of dedicated processors are placed in close proximity to each other. This saves considerable time moving data around and makes it possible for the processors to work together, for example in mesh and hypercube architectures. The use of multi-core processors combined with centralization is an emerging trend. One can think of this as a small cluster that both depends upon and contributes to the cloud. Supercomputers play an important role in the field of computational science, and are used for a wide range of computationally intensive tasks in various fields, including quantum mechanics, weather forecasting, climate research, oil and gas exploration, molecular modeling, and physical simulations. Throughout their history, they have been essential in the field of cryptanalysis. History. The history of supercomputing goes back to the 1960s, with the Atlas at the University of Manchester and a series of computers at Control Data Corporation, designed by Seymour Cray. These used innovative designs and parallelism to achieve superior computational peak performance. The Atlas was a joint venture between Ferranti and the Manchester University and was designed to operate at processing speeds approaching a near microsecond per instruction, about a near million instructions per second. The first Atlas was officially commissioned on 7 December 1962 as one of the world's first supercomputers, considered to be the most powerful computer in the world at that time by a considerable margin, and equivalent to 4 IBM 7094s. The CDC 6600, released in 1964, was designed by Cray to be the fastest in the world by a large margin. Cray switched from germanium to silicon transistors, which he ran very fast, solving the overheating problem by introducing refrigeration. Given that the 6600 outran all computers of the time by about 10 times, it was dubbed a supercomputer and defined the supercomputing market when 100 computers were sold at $8 million each. Cray left CDC in 1972 to form his own company. 4 years after leaving CDC, Cray delivered the 80 MHz Cray 1 in 1976, and it became one of the most successful supercomputers in history. The Cray 2 released in 1985 was an 8-processor liquid-cooled computer and fluorinet was pumped through it as it operated. It performed at 1.9 GHz and was the world's fastest until 1990. While the supercomputers of the 1980s used only a few processors, in the 1990s, machines with thousands of processors began to appear both in the United States and in Japan, setting new computational performance records. Fujitsu's numerical wind tunnel supercomputer used 166 vector processors to gain the top spot in 1994 with a peak speed of 1.7 GHz per processor. The Hitachi Senior 2201 obtained a peak performance of 600 GHz in 1996 by using 2048 processors connected via a fast three-dimensional crossbar network. The Intel Paragon could have 1,000 to 4,000 Intel i860 processors in various configurations, and was ranked the fastest in the world in 1993. The Paragon was a MIMD machine which connected processors via a high-speed two-dimensional mesh, allowing processes to execute on separate nodes. Communicating via the message passing interface. Hardware and architecture. Approaches to supercomputer architecture have taken dramatic turns since the earliest systems were introduced in the 1960s. Early supercomputer architectures pioneered by Seymour Cray relied on compact innovative designs and local parallelism to achieve superior computational peak performance. However, in time the demand for increased computational power ushered in the age of massively parallel systems. While the supercomputers of the 1970s used only a few processors, in the 1990s, machines with thousands of processors began to appear, and by the end of the 20th century, massively parallel supercomputers with tens of thousands of off-the-shelf processors were the norm. Supercomputers of the 21st century can use over 100,000 processors connected by fast connections. Throughout the decades, the management of heat density has remained a key issue for most centralized supercomputers. The large amount of heat generated by a system may also have other effects, for example reducing the lifetime of other system components. There have been diverse approaches to heat management, from pumping fluorinet through the system, to a hybrid liquid air cooling system or air cooling with normal air conditioning temperatures. Systems with a massive number of processors generally take one of two paths. In the grid computing approach, the processing power of a large number of computers, organized as distributed, diverse administrative domains, is opportunistically used whenever a computer is available. In another approach, a large number of processors are used in close proximity to each other, for example in a computer cluster. In such a centralized massively parallel system, the speed and flexibility of the interconnect becomes very important, and modern supercomputers have used various approaches ranging from enhanced infinite-band systems to three-dimensional torus interconnects. The use of multi-core processors combined with centralization is an emerging direction, for example as in the Cyclops 64 system. As the price performance of general-purpose graphic processors has improved, a number of petaflop supercomputers such as Tiani I and Nebulae have started to rely on them. However, other systems such as the K computer continue to use conventional processors such as SPARC-based designs, and the overall applicability of GPGPUs in general-purpose high-performance computing applications has been the subject of debate, in that while a GPGPU may be tuned to score well on specific benchmarks, its overall applicability to everyday algorithms may be limited unless significant effort is spent to tune the application towards it. However, GPUs are gaining ground, and in 2012 the Jaguar supercomputer was transformed into Titan by replacing CPUs with GPUs. A number of special-purpose systems have been designed, dedicated to a single problem. This allows the use of specially programmed FPGA chips or even custom VLSI chips, allowing better price-performance ratios by sacrificing generality. Examples of special-purpose supercomputers include Bell, Deep Blue, and Hydra, for playing chess, Gravity Pipe for astrophysics, NGRABE 3 for protein structure computation, molecular dynamics, and Deep Crack, for breaking the DES cipher. Energy usage and heat management. A typical supercomputer consumes large amounts of electrical power, almost all of which is converted into heat, requiring cooling. For example, Tiani 1A consumes 4.04 megawatts of electricity. The cost to power and cool the system can be significant. For example, 4MW at 10 cents per kilowatt-hour is $400 an hour, or about $3.5 million per year. Heat management is a major issue in complex electronic devices, and affects powerful computer systems in various ways. The thermal design power and CPU power dissipation issues in supercomputing surpass those of traditional computer cooling technologies. The Supercomputing Awards for Green Computing reflect this issue. The packing of thousands of processors together inevitably generates significant amounts of heat density that need to be dealt with. The Cray 2 was liquid-cooled, and used a fluorinet cooling waterfall, which was forced through the modules under pressure. However, the submerged liquid cooling approach was not practical for the multi-cabinet systems based on off-the-shelf processors, and in System X a special cooling system that combined air conditioning with liquid cooling was developed in conjunction with the Liebert Company. In the Blue Gene system, IBM deliberately used low-power processors to deal with heat density. On the other hand, the IBM Power 775, released in 2011, has closely packed elements that require water cooling. The IBM Quasar system, on the other hand, uses hot water cooling to achieve energy efficiency, the water being used to heat buildings as well. The energy efficiency of computer systems is generally measured in terms of flops per watt. In 2008, IBM's Roadrunner operated at 376 flops watt. In November 2010, the Blue Gene Q reached 1684 flops watt. In June 2011, the top 2 spots on the Green 500 list were occupied by Blue Gene machines in New York with the Dejima cluster and Nagasaki placing third with 1375 flops W. Software and System Management, Operating Systems. Since the end of the 20th century, supercomputer operating systems have undergone major transformations, based on the changes in supercomputer architecture. While early operating systems were custom-tailored to each supercomputer to gain speed, the trend has been to move away from in-house operating systems to the adaptation of generic software such as Linux. Since modern massively parallel supercomputers typically separate computations from other services by using multiple types of nodes, they usually run different operating systems on different nodes, for example using a small and efficient lightweight kernel such as CNK or CNL on compute nodes, but a larger system such as a Linux derivative on server and I/O nodes. While in a traditional multi-user computer system, job scheduling is, in effect, a tasking problem for processing and peripheral resources, in a massively parallel system, the job management system needs to manage the allocation of both computational and communication resources, as well as gracefully deal with inevitable hardware failures when tens of thousands of processors are present. Although most modern supercomputers use the Linux operating system, each manufacturer has its own specific Linux derivative, and no industry standard exists, partly due to the fact that the differences in hardware architectures require changes to optimize the operating system to each hardware design. Software tools and message passing. The parallel architectures of supercomputers often dictate the use of special programming techniques to exploit their speed. Software tools for distributed processing include standard APIs such as MPI and PVM, VTL, and open-source-based software solutions such as Beowulf. In the most common scenario, environments such as PVM and MPI for loosely connected clusters and OpenMP for tightly coordinated shared memory machines are used. Significant effort is required to optimize an algorithm for the interconnect characteristics of the machine it will be run on. The aim is to prevent any of the CPUs from wasting time waiting on data from other nodes. GPUs have hundreds of processor cores and are programmed using programming models such as CUDA. Moreover, it is quite difficult to debug and test parallel programs. Special techniques need to be used for testing and debugging such applications. Distributed supercomputing, opportunistic approaches. Opportunistic supercomputing is a form of networked grid computing whereby a super virtual computer of many loosely coupled volunteer computing machines performs very large computing tasks. Grid computing has been applied to a number of large-scale embarrassingly parallel problems that require supercomputing performance scales. However, basic grid and cloud computing approaches that rely on volunteer computing cannot handle traditional supercomputing tasks such as fluid dynamic simulations. The fastest grid computing system is the Distributed Computing Project Folding at Home. Effort H reported 43.1 petaflops of x86 processing power as of June 2014. Of this, 42.5 petaflops are contributed by clients running on various GPUs, and the rest from various CPU systems. The BOINC platform hosts a number of distributed computing projects. As of May 2011, BOINC recorded a processing power of over 5.5 petaflops through over 480,000 active computers on the network. The most active project, Milky Way at Home, reports processing power of over 700 teraflops through over 33,000 active computers. As of May 2011, GIMPS's distributed Mersenne prime search currently achieves about 60 teraflops through over 25,000 registered computers. The Internet Prime Net server supports GIMPS's grid computing approach, one of the earliest and most successful grid computing projects, since 1997. Quasi-opportunistic approaches. Quasi-opportunistic supercomputing is a form of distributed computing whereby the a super virtual computer of a large number of networked geographically dispersed computers performs huge processing power demanding computing tasks. Quasi-opportunistic supercomputing aims to provide a higher quality of service than opportunistic grid computing by achieving more control over the assignment of tasks to distributed resources and the use of intelligence about the availability and reliability of individual systems within the supercomputing network. However, quasi-opportunistic distributed execution of demanding parallel computing software in grids should be achieved through implementation of grid-wise allocation agreements, co-allocation subsystems, communication topology-aware allocation mechanisms, fault-tolerant message passing libraries and data preconditioning. Performance measurement, capability versus capacity. Supercomputers generally aim for the maximum in capability computing rather than capacity computing. Capability computing is typically thought of as using the maximum computing power to solve a single large problem in the shortest amount of time. Often a capability system is able to solve a problem of a size or complexity that no other computer can, for example a very complex weather simulation application. Capacity computing, in contrast, is typically thought of as using efficient cost-effective computing power to solve a small number of somewhat large problems or a large number of small problems, for example many user access requests to a database or a website. Architectures that lend themselves to supporting many users for routine everyday tasks may have a lot of capacity, but are not typically considered supercomputers, given that they do not solve a single very complex problem. Performance metrics. In general, the speed of supercomputers is measured and benchmarked in FLOPS, and not in terms of MIPS, that is as instructions per second, as is the case with general-purpose computers. These measurements are commonly used with an SI prefix such as tera, combined into the shorthand petaFLOPS, or peta, combined into the shorthand FLOPS. Petascale supercomputers can process 1 quadrillion FLOPS. Exascale is computing performance in the exaflops range. An exaflop is 1 quintillion FLOPS. No single number can reflect the overall performance of a computer system, yet the goal of the LINPACK benchmark is to approximate how fast the computer solves numerical problems, and it is widely used in the industry. The FLOPS measurement is either quoted based on the theoretical floating point performance of a processor, which is generally unachievable when running real workloads, or the achievable throughput, derived from the LINPACK benchmarks and shown as RMAX in the TOP 500 list. The LINPACK benchmark typically performs LU decomposition of a large matrix. The LINPACK performance gives some indication of performance for some real-world problems, but does not necessarily match the processing requirements of many other supercomputer workloads, which for example may require more memory bandwidth, or may require better integer computing performance, or may need a high-performance I/O system to achieve high levels of performance. The TOP 500 list. Since 1993, the fastest supercomputers have been ranked on the TOP 500 list according to their LINPACK benchmark results. The list does not claim to be unbiased or definitive, but it is a widely cited current definition of the fastest supercomputer available at any given time. This is a recent list of the computers which appeared at the top of the TOP 500 list, and the peak speed is given as the RMAX rating. For more historical data, see History of supercomputing. Applications of supercomputers. The stages of supercomputer application may be summarized in the following table. The IBM Blue Gene P computer has been used to simulate a number of artificial neurons equivalent to approximately 1% of a human cerebral cortex, containing 1.6 billion neurons with approximately 9 trillion connections. The same research group also succeeded in using a supercomputer to simulate a number of artificial neurons equivalent to the entirety of a rat's brain. Modern-day weather forecasting also relies on supercomputers. The National Oceanic and Atmospheric Administration uses supercomputers to crunch hundreds of millions of observations to help make weather forecasts more accurate. In 2011, the challenges and difficulties in pushing the envelope in supercomputing were underscored by IBM's abandonment of the Blue Waters petascale project. Research and development trends. Given the current speed of progress, industry experts estimate that supercomputers will reach 1 exaflops by 2018. China has stated plans to have a 1 exaflop supercomputer online by 2018. Using the Intel MIC multi-core processor architecture, which is Intel's response to GPU systems, SGI plans to achieve a 500-fold increase in performance by 2018, in order to achieve 1 exaflop. Samples of MIC chips with 32 cores, which combine vector processing units with standard CPU, have become available. The Indian government has also stated ambitions for an exaflop-range supercomputer, which they hope to complete by 2017. Eric P. de Benedictis of Sandia National Laboratories theorizes that a zetaflop computer is required to accomplish full weather modeling, which could cover a 2-week time span accurately. Such systems might be built around 2030. See also, ACMIEEE Supercomputing Conference, Jungle Computing, NVIDIA Tesla Personal Supercomputer, Supercomputing in China, Supercomputing in Europe, Supercomputing in India, Supercomputing in Japan, Ultra Network Technologies, Testing High-Performance Computing Applications, Notes and References.